Welcome to this next video in which we are discussing direct sums of subspaces. Okay, so we've now seen the two important concepts that we need to know in order to understand what a direct sum of subspaces is. Okay, and those two important concepts are, number one, what it means to sum up a bunch of subspaces, and secondly, what it means for a collection of subspaces to be independent. Okay, so now let's simply define what is meant by a direct sum of subspaces. So a direct sum is just a special case of a sum. Okay, it's just the sum of a bunch of subspaces when they are independent. Okay, so if you have a collection of subspaces W1, W2, all the way up to Wn, which are independent, so these are independent, then if you want to sum these subspaces up to create the new subspace of the vector space capital V, okay, then we call it a very special sum, and it's called the direct sum of these independent subspaces. But it's exactly the same definition as before. It's just a special case of it where the subspaces that we're summing up are independent, and it's actually denoted with a separate symbol. What we do is we put all of the plus symbols in circles like so, and write the subspace capital W1 circle plus the subspace capital W2, etc., all the way down to the subspace capital Wn. Okay, so a direct sum then, it is just the sum of a bunch of subspaces when those subspaces are independent. So it's a different name for the same concept, but it's a special case of that concept where the subspaces are independent. Okay, so that then is what is meant by the direct sum of a bunch of independent subspaces. It's just the sum of those independent subspaces. So I'll write out the definition here. It's just the set that consists of all things of the form little w1 plus little w2 plus all the way up to little wn, where these little wi's are elements of the capital Wi. Okay, and it turns out that when you have when you sum together subspaces that are independent, it's far more interesting. What you get is far more interesting than what you would get if you're summing up subspaces that aren't independent, which is why direct sums are more interesting than sums of subspaces. Okay, these are the special sums where it's actually going to be very interesting. Okay, right. So what I want to do then is, firstly, I want to talk about how the example that we did earlier of a sum of two subspaces, that was actually a direct sum because those two subspaces that we had were actually independent. So we could have said that that was the direct sum of those two subspaces. So I'll just get the example back up again. So here was the example, remember, it was an example from R2, and the two subspaces we were using were capital W1 was this subspace which was the span of the vector 2, 1, so all scalar multiples of this vector 2, 1, and that's this orange line here. And capital W2 here, that's the span of this vector 0, 1, and that of course is the red line here. Okay, now hopefully it should be obvious that these two subspaces here, capital W1 and capital W2, are independent, because what did we show is the equivalent statement to just two subspaces being independent. We showed that equivalently you can say that the intersection of those two subspaces just contains the zero vector, and hopefully from the picture it should be very obvious that those two subspaces, the only thing that both of them contains is the zero vector. Okay, so the intersection of those two is just going to be the zero vector. So those two are indeed independent, and this in fact was a direct sum then. So we could have put a circle around there. It was a special sum because both of the subspaces were independent from one another. Okay, so to give you a bit of intuition then for what happens when you take a sum of subspaces which aren't independent, let's now do an example of where we're going to sum two subspaces which are not independent together, and we'll see how something far less interesting happens. Okay, so I want a subspace which is dependent or non-independent with this subspace capital W1. Okay, and a subspace of that form is going to have an intersection that is not just the zero vector. Okay, now we know subspaces of R2 are very simple, okay? There is the zero subspace, which is a single point. Then there are the subspaces which are all lines which go through the zero vector, which is the span of a single vector. And then finally there's the entire vector space itself. Okay, so if we want another subspace which doesn't just have the zero vector as its intersection, we don't really have that much choice. We either need the exact same thing, the same line which goes through the origin, okay, or we need the entire vector space R2. Okay, so let's just try adding a subspace to itself. Let's try adding the subspace W1 to itself, okay, and those two subspaces are certainly not independent because, as I say, their intersection is obviously just equal to W1 itself. Okay, now what happens if we do that then? Well, we will be considering all things of the form little w1 plus little w1 again, where little w1 is an element of capital W1. Now, of course, when you add together any two elements of, and I should put a bar potentially over that because they don't necessarily have to be the same. You've just picked some element from capital W1 and you've added it to another element of capital W1. Okay, so W1 and W1 bar are elements of capital W1. Okay, so you're adding any two elements of that subspace capital W1 together, but of course you're not going to get something that's outside of capital W1 when you do that. Okay, you're just going to get capital W1 back again here. Okay, because all the elements of this form will be in capital W1, and you can certainly get absolutely all the elements of capital W1, because if you like, you can just set W1 bar here equal to the zero vector, and then you can let little w1 here equal whatever you want, and then get every single vector in capital W1. Okay, so there, the summing together hasn't had that much effect at all, okay, and that's because these two subspaces were not independent. Okay, so really summing subspaces together is only interesting when they're independent. Okay, it's far more interesting and far easier to characterize if you are summing together independent subspaces, because then what we know is that all the different combinations of vectors that you can choose from the different subspaces are going to give you different vectors in the vector space, so you don't have any degeneracies. The problem here is that you're going to have loads of different combinations here which are all going to give the same answer, and that's why this set hasn't got any bigger basically than the original subspaces that you were adding together. So the fact that they're independent, when you add independent subspaces together, will ensure that the sum is always going to be bigger in some sense. Okay, you're always going to get new elements because all of the different combinations have to give a new separate vector in the larger vector space capital V. You're never going to have some element of the vector space being added more than once by different combinations. Okay, so that's the importance then of trying to sum together independent subspaces, and when your subspaces that you're adding together are independent, then we promote the symbol from just being represented as a plus to being represented as this plus with a circle around it, and that's called a direct sum. Okay, so that then is what the direct sum of subspaces within a vector space actually means. Okay, finally, what I want to end this video with is a very useful and important theorem that is very, very easy to prove. Okay, you shouldn't be intimidated by this theorem, but the notation is going to be quite cumbersome. Okay, so the theorem that we want to prove then is if we have a bunch of subspaces, capital W1, capital W2, all the way up to capital Wn, so these are all subspaces of my vector space capital V, okay, and they're all going to be independent, okay, so they're all independent, and let's say I have a basis for each one of them, so they're all subspaces of some finite dimensional vector spaces, assumption that we're going to have to make at this point. Okay, so V is finite dimensional, let's say. Okay, and all of these subspaces are then going to be finite dimensional as well as soon as V is finite dimensional. Okay, so all of them can then have a basis, because we know that for any finite dimensional vector space it's always possible to find a basis. So W1, let's say it has a basis B1, W2, let's say it has a basis B2, all the way up to Wn, which we'll say has a basis Bn. Okay, so we've got some basis for every single one of these subspaces. My claim then is that if these are all independent, then this new subspace that you construct by taking the direct product of all of them, okay, so W1 direct producted with W2 all the way up to plus Wn, my claim is that I can construct a basis for this new subspace here, which is the direct product of all of these independent subspaces, by taking the union of all of these bases. Okay, so what I'm going to do is I'm going to construct a master basis, the basis for this new thing that I've constructed here, by unioning together all of these bases here. So I'm going to union from I is equal to 1 to n, the bi's, join together all of these bases, and my claim is that that new set will be a basis for this. Okay, so I agree that when you first see this it looks like a bit of a nightmare, okay, because you know, if you've got new symbols galore here, okay, you've got a complicated symbol here as well, so it doesn't look easy to prove, but this is an incredibly simple theorem, okay, but as I say, the notation is going to be quite cumbersome, okay, and it's going to get even more cumbersome now, because what I'm going to do is create some notation for the actual vectors in these bases for the subspaces that are independent here, which we're going to direct sum, okay, because this is going to be really important, but this notation is going to be cumbersome. But don't worry, the theorem itself is very, very simple and very easy to prove. Okay, it's just the notation that's difficult. Okay, so B1 here, okay, I'm going to create then an explicit set of vectors which is going to be my basis B1 for this subspace capital W1. Okay, and the way I'm going to do this is I'm going to have two subscripts, two indexes. Now the first index is going to tell me which subspace this is in the basis of. Okay, so this 1 here denotes the fact that it's in the subspace W1, okay, and it's going to be in the basis capital B1. The second subscript, the second index here, is going to denote which actual vector it is in this basis B1. Okay, so we'll have V1, 1, then we'll have V1, 2, and we'll go all the way along until we have V1, and then how far does it go up? Well, it's going to go up the dimension of W1, and I'm just going to denote that M1. Okay, so M1 is just a number that's associated with this vector space capital W1, and it's the dimension of that vector space capital W1. So I'll make that explicit. M1 here is just the dimension of W1. Okay, so how many vectors you need in a basis for W1. Okay, so there is my explicitly written out basis for capital W1. Now we're not going to stop there, I'm going to do it for B2 and Bn as well. Okay, so B2 next. So B2 here, I'm going to write B2 explicitly out, and the way it will work, I will now raise this first index to 2. So we'll have V2, 1, V2, 2, and it will go on all the way up until V2, and then it will go up to the dimension of W2. So I'll denote that M2. Okay, so there's not necessarily the same number of vectors in this basis B1 as there are in this basis, because we don't know that these two subspaces W1 and W2 have the same dimension. Okay, so M2 here is going to be the dimension of W2 here. Okay, right, so there is my basis B2 written explicitly out, and of course I can continue this on. Okay, so this goes on and on all the way up until Bn here, and if I write Bn explicitly out, it will have Vn, so I've moved this subscript up to n now because it's the basis for the vector space Wn, and then we'll have n1, Vn2, and that will go all the way up to Vn, and then we'll have the dimension of the vector space Wn, so it'll be Mn now. Okay, so Mn here is the dimension of Wn. So more generally then, Mi is equal to the dimension of Wi. Okay, that's how it works. Right, so here now I have got my explicitly written out bases, and this is as cumbersome as the notation gets. So as long as you're fine with that, then this proof is now going to be incredibly simple. Okay, so my claim is that if I union all of these sets together, so I union this one with this one all the way up to this one, I will get a basis for my direct sum of W1 with W2 all the way up to Wn. Okay, so the first thing that I want to make absolutely crystal clear is that all of these bases are, they will have empty intersections with one another. Okay, so what I mean by that is there's going to be no duplicates. There's not going to be a vector in here also in here. Okay, so it won't be the case, for instance, that v12 is the same vector as v2m2. Okay, they all have empty intersections. So if you pick any two of these, their intersection is empty. So I suppose I could write this out formally like this. bi intersect bj is equal to the empty set for all I is not equal to j. Okay, so you pick any two bases, obviously don't pick the same one, and intersect them, and the intersection is the empty set. There's no vector that's in both of them. So let me just explain exactly why that is going to be the case. Okay, what comes from the fact that these two, these subspaces, W1, W2, all the way up to Wn, they are independent. We said they were independent, and remember what that means. That means that if I take a combination of vectors from them, W1, W2, plus all the way up to Wn, the only way that I can get a combination that will sum to give the zero vector is if all of them are the zero vector, if you pick the zero vector from all of the subspaces. Now, if there was some basis vector that was in two of these different bases, okay, so let's say v was in b1 here and it was in b2, then it would certainly be an element of w1 and w2, because after all, a basis of a vector space is just a subset of the elements of that vector space. So for instance, if I had a little v which was an element of b1 and v was an element of b2, okay, so it was in both of these bases. I'm just picking b1 and b2 arbitrarily, it could be more general. Okay, then what that instantly implies is that v is in w1 and v is in w2. So what that then means is the additive inverse of v is in both w1 and w2, because these are after all subspaces. But then what I can do is I can say, okay, pick as your little w1 here v, and pick as your little w2 negative v, and then pick as all the other little w's 0, and then I've found a non-trivial combination of vectors from my subspaces which will sum to give the zero vector. Okay, so that will contradict them being independent. So what I've just shown you there is that all of these bases, they all contain distinct elements. Okay, so when I union them together, no element in this final thing is going to have been put in more than once. Okay, they're all separate sets basically. They all have empty intersections with other bases. Okay, right. So that's the first thing. So that's an understanding point, that we are literally just going to end up with all of these vectors plus all of these vectors plus etc. all the way to this one here, and they're all going to be separate. Now what I want to show you is that this actually spans this entire subspace here, the direct product of W1 with W2 all the way up to Wn, and that it is linearly independent. Okay? So, firstly, let's take on the fact that it spans this entire direct product here. Okay, sorry, direct sum, not direct product. Okay, so, what I want to do then is take an arbitrary element in here and prove that I can write it as a linear combination of the vectors in this basis B. Okay, so let's take an arbitrary vector from here, and an arbitrary vector from here is something of the form little w1 plus little w2 plus all the way along to little wn. Okay, anything in there can be written in this form, okay, in one and only one way, because remember, capital W1, capital W2, all the way up to capital Wn is independent by assumption. Okay, right, so here is our arbitrary element of this direct sum. What I now want to do is split it into a linear combination of the basis vectors. Well, the way I can do this is I can split each one of these into a linear combination of the basis vectors from that subspace. Okay, so the little w1 here, that is an element of my subspace capital W1. Any element in capital W1 can be written as a linear combination of the basis vectors in capital B1. Okay, here. So what that means then is I can write little w1 like so as, and I'll just make sure this is in view, a linear combination of the basis elements here. So I'm going to have the same indexes going with my scalar coefficients as I have going with the basis vectors here. So it'll be c11 times v11 plus c12 times v12 plus all the way up to c1, and then we'll need m1 v1 m1. Okay, so remember, this may look horrendously complicated, but this is just saying I can write little w1 as a linear combination of these basis vectors, which of course I can do because that is after all the basis of capital W1, and little w1 is just an element of capital W1. Okay, so there's little w1 done. Now let's do little w2. So little w2 is an element of the subspace capital W2. Capital W2 has this basis capital B2 here. Okay, so any element in capital W2 can be written as a linear combination of the elements in this basis B2. Okay, so let's add this in. So it'll be C21 times V21 plus C22, again sticking with the same indexes, V22 plus all the way up to C2M2 V2M2. Okay, and all of theseCij's, they are all going to be elements of the field. I'll just remind you of that. Okay, so there we've now added in little w2 here, and then we'll continue on. So we'll go plus dot 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 all the way up to Wn here, and of course now Wn is an element of capital Wn, so it can be written as a linear combination of these basis vectors in the set Bn, which is a basis of capital Wn. So we'll write it like so. We'll get Cn1 times Vn1 plus Cn2 times Vn2 plus all the way along to Cnmn times Vnmn, like so. And of course, what we have now got is a great big linear combination of all of the basis vectors that are in this set capital B here. Okay, we have just got a linear combination of all of the vectors that are in there. Okay, so bravo, we have taken any vector in this direct sum of capital W1 with capital W2 with capital Wn, and we have written it as a linear combination of the vectors in B. Okay, so very, very simple. We've just used the fact that all of these are bases of these separate subspaces which we've summed together. Okay, so now the slightly more difficult one, not that much more difficult, still very easy, but slightly more difficult nonetheless, is to prove that this set is actually linearly independent. Okay, so what we want to prove then is that there is only one linear combination of all these vectors which gives the zero vector, and that is the linear combination where all of these coefficients here are going to be the zero from the field. Okay, so I might as well use this exact thing that I've written out here. After all, this is just a massive great linear combination of all my vectors in B. Okay, so to avoid having to draw this entire thing out again, we are looking for a linear combination which gives us the zero vector, and we are trying to prove then that the only such linear combination which will do that is the one where all of these coefficients in front of all of these vectors are the zero in the field. So how are we actually going to do that? Well, we're going to do it by proof by contradiction. So we're going to assume the exact opposite of what we want to prove, and we're going to disprove something that we assumed. Okay, so we're going to assume now that there is a non-trivial linear combination of these vectors in that set capital B, which gives me the zero vector, i.e. not all of these coefficients are equal to zero in the field. There are some non-zero scalars in this great big linear combination here. Okay, right, so what now can we do? Well, what we can now do is say these bits that I've got underlined in the different colours, this orange bit, this green bit, this turquoise bit, these are all elements of my different subspaces which I've direct summed together to get my direct sum subspace. Okay, so this is an element of capital W1 here in orange. This is an element of capital W2 here in green. Okay, and this is an element of capital Wn here in turquoise. Okay, so whenever you have a linear combination of the vectors in this set capital B, you can always think of it in this way, as part of it makes up something in capital W1, part of it makes up something in capital W2, etc., all the way down to a part of it that makes up something in capital Wn. Here's the part that where you use the fact that these subspaces are all independent. We know that because these subspaces are all independent, that the only way you can get something in capital W1 adding to something in capital W2, going all the way up to adding something in capital Wn, and it give the zero vector, is if all of these are equal to the zero vector. So that tells us that this orange thing has to equal the zero vector, that tells us that this green thing has to equal the zero vector, and that tells us that this turquoise thing has to equal the zero vector. Okay, so I hope you've understood what my argument is here. If I take any linear combination of the vectors in that set capital B, I can always think of this as just being an element of capital W1 plus an element of capital W2 all the way up to plus an element of capital Wn, just by collecting the vectors in capital B together, which came from the same basis for the same subspace. Okay, so that's my argument here. So I'm now saying that if I have something that's going to equal the zero vector here, all of these different bits, this orange bit, this green bit, and this turquoise bit, they must all equal the zero vector. Okay, but that's now a problem, because we know that those basis vectors in the subspaces are linearly independent, okay, which means that the only linear combination which can actually give the zero vector is going to be the trivial one, where all of the coefficients are zero, and that's true for each of these. That argument works in all of these because they're all bases of those subspaces. Okay, so that tells us that to do this, all of these coefficients would have to be zero, but that's a contradiction. That contradicts our initial assumption that we were going to assume that we had a non-trivial linear combination. Okay, so here is the argument as to why you can only have a trivial linear combination giving you the zero vector in this for this set capital B. Okay, it's because of the fact that the subspaces are linearly the subspaces are independent, so that means that if you're adding an element of capital W1 to an element of capital W2 all the way up to adding an element from capital Wn to get the zero vector, they all have to be the zero vector, and the only way you can get the zero vector from a linear combination of the basis vectors in each subspace is for them to be all have the coefficient 0, basically, for it to be the trivial linear combination. Okay, so that's why it can only be the case that if you have a linear combination of all of these vectors in the set capital B that's equaling the zero vector, it has to be the trivial linear combination where all of the scalar coefficients are 0 in the field. Okay, and hence that proves then that this set capital B is linearly independent. Okay, so overall what that shows is that if you have a bunch of independent subspaces and you're going to direct sum those subspaces together to get a new subspace of the vector space capital V, then if you want a basis for this new subspace, the way that you can do it is just union together bases from each of the independent subspaces that you are direct summing together. And when you actually think about that, that is very, very nice. That's a very, very beautiful theorem. Okay, and I hope that the cumbersome notation has not overwhelmed you, because this proof is very, very simple. The ideas here are not complicated at all. It's not a particularly deep result at all. Okay, so with that then, we will finish this introductory video on direct sums of subspaces in vector spaces.